Let's look at atomic size. We're going to look at some trends in different properties that are present in the periodic table, and one of them is atomic size. Well, how do you define the size of an atom? We typically talk about the atomic radius, so that's from the nucleus to the outside of the atom. But what is exactly the outside of the atom? It's not a little marble with a distinct edge, right? It's those fuzzy electron clouds. So how do you define it? How would you even measure it? There's different ways to measure it. One way is to look at, here we have krypton solid. So we've just got a solid of atoms, and we can measure the distance between two adjacent nuclei. So the distance between this nucleus and that nucleus. And we can assume that those atoms are probably touching each other. And so we could say, well, that distance is twice the radius of one atom. That's known as the van der Waals radius. It's a non-bonding atomic radius. These guys aren't bonding, they're just a solid. We can also look at the distance between nuclei in two atoms that are covalently bonded to each other. We can see from this picture how this bromine atom and this bromine atom, they kind of overlap into each other, right? And so the distance here between this bromine nucleus and the next one is smaller than if we were looking at the atoms in their solid state. But we can measure that distance. It's the length of it's just the distance between the two nuclei. Divide that by 2, and we're going to call that the radius of a bromine atom. But that's a covalent radius or a bonding atomic radius. That's always going to be smaller than the non-bonding van der Waals radius. So we're not going to worry about those details. I want you to know that, yeah, it's kind of not so obvious how we measure those things. We're just going to talk about an average atomic radius based on measuring atoms in different compounds and averaging all of those together. So this is a more general term. It's what we can use to describe the approximate bond length, and we'll learn more about that later. The approximate bond length would just be the sum of the atomic radii of the two atoms that are bonded. That's for covalent bonds. So there are trends in atomic radius. We're just going to look at the main group elements first. And this graph is showing atomic radius versus atomic number. So you might think, well, isn't it just kind of a straight line where the more protons and electrons, the bigger the atom? No, it's not. If we look at these highest ones here, these are the alkali metals. They're in group 1A: lithium, sodium, potassium, rubidium, cesium. Those are in a column in the periodic table, and as we go down the column, the atoms get bigger. And that is true for all of the columns. As you go down, the atoms get bigger. Well, that makes sense. As you're going down, you're filling a higher principal energy level. N is going up. N corresponds to the period. So for lithium has valence electrons in N equals 2. Sodium has N equals 3. Potassium's N equals 4. Each of those layers is larger, so it makes sense that the atoms are getting bigger. We can look at the other extreme, group 8, and here's helium, neon, argon, krypton, xenon. And you see, it's not a straight line, but it is a trend. They increase as you go down. If we look at the trend going across a period, it's a little surprising. So lithium, serious technology issues right now. Okay, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. As we're going across left to right, they get smaller. That's not what I would expect if I didn't know what was going on. But they do, they get smaller, and that's consistent. That's consistent for all these different periods. It gets a little wonky in the transition metals, but we're kind of getting an idea that the transition metals just, they don't quite follow patterns. But for the main group elements, we see they're getting smaller as they go across. Okay, there's a little bit of a glitch there. Just ignore that. So what's happening here? Well, we've got shielding, and we've talked about this. The electrons are attracted to the nucleus, repelled by each other, and the outer electrons get shielded from the nucleus by the core electrons. So those outer electrons don't experience the full strength of the nuclear charge. So here we've got a lithium atom. The nucleus has a +3 charge. Here we have 2 core electrons. Those guys in the 1s are close to the nucleus. And remember, these are not just particles, they really are standing waves. They're occupying this whole space at the same time. So this electron, looking in towards the nucleus, it's got these 2 guys blocking out some of the attractive force of that nucleus. So essentially these guys are taking up 2 of the positive 2 charges and leaving only 1 for this guy. So each of these guys sees +3, he only sees +1. So effective nuclear charge is the charge on the nucleus minus the number of core electrons. We're interested in what effective charge do the valence electrons see. So effective nuclear charge is the actual nuclear charge, which is the same as the atomic number, minus the number of core electrons. Valence electrons do shield a little bit, but we don't have to worry about it in Chem 1A. Okay, so let's look at the effective nuclear charge. I don't want to do nitrogen and argon. I want to do nitrogen. Let's do phosphorus and argon. Let me do phosphorus. So for phosphorus, what is its atomic number? 15. That tells me it has 15 protons in the nucleus. It has a total of 15 electrons. How many valence electrons does it have? 5, because it's in group 5, right? If it has 5 valence electrons, the other electrons must be core electrons, right? So how many core electrons are there? 10. So for phosphorus, we've got 15 minus 10. So the effective nuclear charge is +5. That's what the valence electrons see. Let's do argon. Argon has 18 protons, right? 18 protons, 18 electrons. How many valence electrons does argon have? 8, right? 8 valence electrons, and the same number of core electrons. 10, right? 18 minus 10 is +8. So the valence electrons in phosphorus see a +5 charge. The valence electrons in argon see a +8 charge. +8 is more attractive. Remember we said that the energy of attraction is proportional to Q1, Q2. So if Q1 is the charge, effective nuclear charge on the nucleus, the argon valence electrons have a stronger pull on them. Does that make sense? The valence electrons for both of these are in the 3p sublevel. So they're on the same floor of the hotel. They're roughly the same distance from the nucleus. But then what happens is this positive 8 charge pulls the electrons of argon in tighter than phosphorus does. And so argon is smaller than phosphorus.
Did you say S is the valence electrons?
No, S is the core electrons.
Cool.
So effective nuclear charge, Z effective, is equal to the atomic number minus S, where S is the core electrons. The reason I was talking about valence electrons is because counting core electrons can be a little tricky. Well, you can look at the previous noble gas, but then things get wonky later on. I think it's simpler to look at the total number of electrons. The number of valence electrons is the group number, right? So argon's in group 8, it's got 8 valence electrons. Take the total number of electrons, subtract the valence electrons, those are the core electrons.
Oh, yeah.
Maybe let's, I didn't need to write that, it's up there, I just didn't see it. Yeah. Well, let's do nitrogen, since we were supposed to do nitrogen in the first place. So, how many protons does nitrogen have? 7. It's element number 7, right? So, maybe we'll do this over here. So, it's got 7 electrons. How many valence electrons does nitrogen have? It has 5 valence electrons. Well, if it has 5 valence electrons, the other electrons are the core electrons. 7 minus 5 means there are 2 core electrons. That's S. So for nitrogen, we've got 7 minus 2, so plus 5. Usually, yes, the effective nuclear charge is very similar to the number of valence electrons. But it's also important to understand how that's calculated. That we're looking at the total charge on the nucleus, and then we're saying, well, these core electrons are roughly each blocking out 1 positive charge. So we subtract the core electrons, and then we've got the valence electrons. The effective nuclear charge. Any other questions? So let's just go back to this periodic table real quick. So as we're going across, say, period 2, the effective nuclear charge is increasing, and that's pulling those electrons in tighter to each other, to the nucleus, and so the atom gets smaller. So this slide summarizes, moving down a column, we see that the atoms get larger. The quantum mechanics explains this because the principal quantum number of the valence electrons is getting larger as you go down a column. Larger principal quantum number, larger volume is farther from the nucleus. So we've got larger orbitals, larger atomic radii. Moving across a period, the effective nuclear charge increases, but the principal quantum number is the same. So we've got stronger attraction for those valence electrons, and that pulls them in and causes them to have smaller radii as we go across. Now the transition metals, not as predictable. They do follow that same trend that if you go down in a group, down a column, they will get larger. But going across doesn't really work very well. You can kind of think of them as being roughly the same size. all of the ones in the same period. The valence shell is the ns2. It's not the d electrons. So as you're going across, the effective nuclear charge is essentially the same, because as you're adding electrons, you're adding core electrons, not valence electrons. So the effective nuclear charge is roughly the same. So we should be able to answer questions like this. On the basis of periodic trends, choose the larger atom in each pair if possible. Tin or iodine. So we need a periodic table to do this, and there's not one on the slide, so I'm just going to draw the relative part of the periodic table. So there's tin and there's iodine. They're in the same period. Which one's larger? Tin. Tin is larger because as we go across a period, the effective nuclear charge increases, pulling the electrons in, making the atoms smaller. Going to the right, they get smaller. Yeah, so going to the right, it gets smaller. We're trying to find the larger one. So tin is larger. Germanium or polonium? So here's germanium, here's polonium. So the vertical trend says that which one's bigger? Says that polonium's bigger. But the trend going across says that polonium's smaller. So it does say, if possible. So we could say, not possible. What if you were forced to choose one? I'd go with polonium being larger. Because coming down, polonium's valence electrons are 2 principal quantum numbers higher than germanium. That's adding layers, right? And yes, the effective nuclear charge is larger, but this is only 2 squares to the right. And its electrons were way far out compared to germanium to start with. So I'd put my money on polonium being larger. Okay, chromium or tungsten. So those are transition metals. There's chromium and tungsten. Which one's bigger? Tungsten. Because the trend is they get larger as we go down. Any questions?
So larger as we go down, but not.
But as you go across to the right, it gets smaller. Which is counterintuitive.